We've seen that differentiation can be thought of as an operator, but it's not the only one. Let's look at a few other examples of operators. Now, wait a minute. What's that? What's an operator? Well, an operator is a function of functions. Takes a function in, spits a function out. So, for example, given a function f, one input, one output, the differentiation operator d applied to f gives the derivative. So df at x is really f prime at x. Okay, that's good. But here's another one, the shift operator, capital E. EF evaluated at x gives you f at x plus 1. So what this does is it shifts the graph of f over to the left 1 unit. One of my favorite operators is the identity operator, I. IF is just f. It does nothing. It's a lazy kind of operator, but I love it. Finally, we're going to look at the forward difference operator, denoted capital delta. Delta of f at x is really giving you the difference, f at x plus 1 minus f at x. It's a step difference. Okay, now what is this notation good for? Well, one of the things that it's good for is you can do algebra with operators. It's very simple, very elegant. Let's look at a few examples. So what about the operator e squared? E squared of f evaluated at x is really e of f at x. That's really f at x plus 1, that's f of x plus 2. So you can take higher powers of e. What about negative powers of e? Well, e inverse, or e to the negative 1 of f at x is really f at x minus 1. So instead of shifting to the left, you're shifting 1 unit to the right. Now, why is that the right definition for E inverse? Well, let's think about that. E inverse applied to E of f is really the same thing as E applied to E inverse of f. It's just f. You shift one way, then the other. And one way to write that is that E inverse E is the same as E inverse. That is just the identity. Aha! And once you see that, it starts making sense that there are exponent rules for operators. So, for example, e to the p times e to the q is really e to the p plus q, following the usual exponent laws. Now, at this point, you may have several questions. What do fractional powers of an operator like e look like? What's e to the 1/3? Or how would you compute higher powers of some of the more interesting operators like, say, the forward difference operator, delta? Well, a simple lemma helps out with that last question. Here's the result. Delta is really e minus I. That is, it's the difference between these two operators. Now, how do you prove something like that? Well, let's go slowly. So by definition, delta of f at x is f at x plus 1 minus f at x, right? Right. Okay, but by definition, f at x plus 1 is really ef at x, and f of x can be thought of as if at x because the identity does nothing. Now, factoring out those operators gives us quantity e minus I applied to f. And because these two operators, delta and e minus I, applied to f evaluated at x gives us the same thing, they are the same operator. Now, this is nice, and it allows us to define and compute higher powers or higher difference operators. So, for example, delta to the 4th, that is delta, 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 delta. That is really quantity e minus I to the 4th. Expanding that out, just as if it were a polynomial, gives us e to the 4th minus 4e cubed plus 6e squared minus 4e plus I. Now, how did I get that? Well, I got that by the binomial theorem. Let's recall the binomial theorem. You hopefully have seen this at some point, maybe in the distant past. This says that quantity a plus b to the n is really the sum, as k goes from 0 to n, of n choose k, a to the n minus k times b to the k, where by n choose k, I mean the binomial coefficient, n factorial, divided by quantity n minus k factorial times k factorial. Now, you may or may not recall having seen the binomial theorem. It applies not only to numbers and to variables, but to operators as well. If you don't recall seeing that, you're going to want to take a moment and review it before moving on, because it's going to be very helpful in the next wonderful exponential lemma. Here it is. This is what we've been working towards. Lemma. The shift operator is the exponential of the derivative. That is, if I take the differentiation operator d, exponentiate it, what I get is the shift operator. Now, what is that? How do we prove something like that? Well, let's, again, go carefully. What we're going to do is write out the definition of the exponential of the differentiation operator. So e to the d applied to f at x is really what? Well, you know what happens when we exponentiate anything. We get the sum as k goes from 0 to infinity of 1 over k factorial times, in this case, d to the k. Now that's the kth derivative. I apply it to f, and then I evaluate all of that at x. Now, I'm going to do one little simple trick, and that is I'm going to take each of those terms and multiply by 1. Or rather, 1 to the k, which is always equal to 1. Now, why am I doing that? I'm doing that because if you remember your Taylor series, then you recognize this as the Taylor expansion of f about x used to evaluate f at x plus 1. And what is f at x plus 1? That's really ef at x. So these two operators, e and e to the d, really give you the same result. They are the same operator. Now, I love this lemma. It is not only lovely, it is also useful. So don't forget it. We're going to use it. Now, this may seem weird, and in fact, it is kind of a weird result, but listen to me carefully. Understanding operator algebra and the exponential lemma is going to be very, very important to us later on, and it's no accident that Taylor expansion is the key to this last result.